Okay, calculate time dilation and explain light clocks, as well as the twin paradox. And I've got paradox in air quotes there for a reason. So this is all 6.2. It is very possible that after going through this, you'll have no idea what's going on. You'll just be totally confused. That's perfectly normal. It may take a couple of viewings of this and the other stuff that I'm going to link to get it at least partially straight in your head. This is definitely counterintuitive stuff, so you're within good company if this doesn't go so well on the first run. So, stuff that we want to remember. Einstein's postulates, there's only two, which makes it easy. All inertial frames are valid. So, in other words, so long as your frame is not accelerating, it is valid, and that means you can run your normal laws in there. Second part, all observers see light travelling at c. So that doesn't matter if you're in A's frame, B's frame, C's frame, D's frame, doesn't matter whose frame you're in, they are all going to see light travel at the speed of light, which is roughly 3 times 10 to the 8 meters per second. Beautiful. Okay, so I've got a rocket travelling past Earth at 50% the speed of light, so 1.5 times 10 to the 8 meters per second. Cool. All right, they're both going to shoot off some laser pulse, and we'll say that this one travels for a second in Earth's frame. So we end up, great, that's going to be 3 times 10 to the 8 meters that's going to travel during that second of Earth's time. Cool, well how far would this one travel? Well, hang on, it's light, but hang on, does that add the extra 50%? So is it going 150% light speed or anything? No, I've got to remember this. This, according to Earth, will travel 3 times 10 to the 8 meters in 1 Earth second. Okay, so don't just add up velocities, because very quickly you can go beyond the speed of light and then you're really confused. Beautiful. Okay, going down to this. We've got what we're going to call light clocks, which are more of a thought experiment object, not an actual object. The basic idea is you have two perfectly reflective surfaces and you can fire a pulse of light and it will just go up and down in these, and then you count one moment either as an up and a down or just as an up, it doesn't really matter. So it's 1 moment to get to the other side. So 1 moment, 2 moments, 3 moments, 4 moments, da 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 da. Just bounces up indefinitely. Brilliant. Well, let's say that we're on the rocket ship, cool, and we're going to fire up a pulse of light, so it goes up 1 moment. Now, because this is fiddly and I'm just going to draw over myself, right now I'm just going to draw it down for the next moment, then up for the next moment, then down for the next moment. Beautiful, okay? Well, we're just going to describe those as moments for now. Cool, so there's a whole, so the light just travels straight up, straight down, and that's it. Nice, boring, easy. Okay, well, how does the rocket ship see a light clock on Earth? Okay, so Earth's going to start his pulse here. Keep in mind that as the rocket ship goes that way, it's going to see Earth as going this way. So the light clock, even though if it's on Earth, it'll just be shooting up and down, from the perspective of the rocket, this thing's going to look like it's shooting up and back. And so that's going to be its first, then back down, so up, down, so on, so on, so on to infinity. Okay, brilliant. Now, it's not moving in the light clock is moving along with it, but it's just easier to draw this way. Okay, well great, so what? What does that mean? Well, we know that light has to travel at c regardless of whose frame you're in. So if these light clocks have the same height, and let's say they were built both on Earth and then one was shipped up to the craft and then it's taken off and then come past Earth again at half the speed of light, so we know that they all measure the same in the same reference frame. Well, then that means that in order to have a moment here, it needs to travel straight up and down. But in order to have that same moment here, it has to travel a diagonal, which necessarily must be longer. So 1 moment for the spaceship seems to be shorter than 1 moment for the clock on Earth. Well, that's interesting. How did that happen? Well, let's flip it around for a second, and let's say, instead of going that way, let's look at things from Earth's perspective. So now Earth is down on the bottom. Let's add a light pulse. Cool, this thing's just going to go up and down, so it'll go up, bounce off the top, so that I'm not just going over the top of myself, comes down, then up, and then down, ad nauseum. How does it see the clock on the spaceship? Well, it sees it let out a burst of light, but the spaceship is drifting across. So, since it's shot up in terms of the spaceship, it's actually going to drift across as we go. So we'll get something like that, and so on. So very, very similar, just reversed. Well, hang on, that means that this thing now has a shorter duration than this thing. Well, hang on, 2 seconds ago we said it was the other way around. What's going on here? Something's a little bit weird. Okay, well, something seems very, very sus about this. And that's because we've moved into time dilation problems with special relativity. And when I say problems, it's a problem with the human, not with the theories. So, something that I want you to consider. Something that I want you to consider. Imagine you've got an x direction and a y direction, and you can only move for so much of time, or at such a speed. Let's say, actually, that's a better idea. Let's say we can only move so fast. Cool, alright, well, I could move perfectly in the x direction for the full duration, or I could move perfectly in the y direction for the full duration, and getting rid of any objects in the way or anything like that. I'd be able to travel the same amount of distance in the x, or in the y. X or y, I should say, sorry. Cool, alright, well, what if I went on some sort of diagonal? Well, necessarily, if I'm travelling at the same speed on all three, that red guy that's on the diagonal, he necessarily can't travel as far on the x as the purple line on the bottom, and he necessarily can't travel as high on the y-axis as the blue line. So he's going to be somewhere in between. Well, why do I bring that? It's like pretty obvious. What I'm trying to say is that if you move through just one dimension, you can maximize in that one dimension. But as soon as you're moving through 2 dimensions, you have to give up some progress in one dimension to make progress in another dimension. And the more you want to move in one dimension, you have to give up even more out of the other dimension. Cool, alright, well that's that. What if we change the idea of x and y into x and time, where x can represent any direction in space? Well, okay, so now I'm giving up movement. So if I have no movement through space, I'm only moving through time. Okay, fine. If I only move through space, I'm experiencing no time. And if I move at some amount through space and some amount through time, then I'm on the red one. So, what's this all talking about? Well, depending on how fiddly you want to get with it, this blue is when you're staying stationary, which is your world line. The purple is the speed, is what light experiences. So light experiences no time. And in between is something that you see as moving relative to you. Now that's all getting a wee bit fiddly. And unsurprisingly, the intuition at this point really begins to break down a fair bit until you've had a bit of practice. So, what's going on here? What does that tell us? Well, that tells us that depending on whether or not you consider yourself stationary, you're going to, well, not even if you consider yourself, you will always consider yourself stationary and be able to say, oh, everything else is moving around me, so long as you're in an inertial frame. Because it's perfectly valid for you to say, I'm stationary, everything's moving, or for everything else to say, no, you're moving, I'm stationary. Both are perfectly valid. There's what are called the Lorenz Equations, which are the bigger version of these. They give you the full mathematics of it. That's outside this course, unfortunately. They resolve all of the little nitty-gritty details. For us, it's going to be suffice to say, if you are, we'll work through it. So this guy is called gamma. It's the Lorentz Factor. It's got 1 over root 1 minus the velocity of whatever the object moving is, squared, over speed of light squared. because you've got 1 minus this thing being divided by the speed of light, and nothing can go faster than the speed of light, this thing is always less than 1. So you've always got 1 minus something here. So this whole thing will always be getting, if this is 0, then you just got 1 over 1, which is fine. And as v gets bigger, this whole thing will get bigger. So your Lorentz factor is always greater or equal to 1. Okay. Brilliant. Now, something that's to be considered is that as an object moves relative to you, you will perceive its time as ticking slower. So, as we view, if we're on Earth and we're viewing this object going past us at half the speed of light, we're going to observe its clock going slower. Now, the notation with this can get very clumsy very quickly, and I don't particularly like some of the names of it, but we're kind of stuck with them. So, we've got t and we've got t sub 0. Sometimes you'll have primes instead of sub-zeros. Same basic ideas. Okay, so t I'm going to call stationary time. It's for the person that thinks they're stationary and they're seeing the object of interest go past. So they see the event moving. T0 is called the proper time, which is a horrible name because there's no such thing as proper time. It just depends on your perspective. That's the time in the frame of the moving event. So if you're in the rocket ship, right, and you're watching the clock in the rocket ship, then you're experiencing proper time. As a general rule, normal t, if you point at the object, you're going to point at the object and your arm will move. If you're in T0, you point at the object of interest and it doesn't move. That's the easiest way I can think of to figure out which one's which. There are a couple of other ways that you can do it, but it's usually backwards engineering it. So let's try to do a little bit of thinking on it. Let's say we've got 5 seconds on Earth. So a clock on Earth registers 5 seconds. How much time goes past on the rocket? Okay, so the first thing we have to realize is, okay, which one are we considering the proper time? Well, if I'm on Earth and I'm pointing at the clock that's ticking off 5 seconds, it's 5 seconds on Earth, so the clock must be on Earth. So I'm on Earth, I'm pointing at this thing, it's not moving, so Earth counts as the proper time for this guy. So T0 equals 5, and we want T. Okay, what colour do I do? Let's go purple. Cool, alright. We had our rocket, and this rocket is this guy. His velocity is c divided by 2. Now very commonly you'll see all your velocities given as some fraction of c, just because it makes the math a lot easier. You can switch it out to 3 times 10 to the 8, but you're going to be causing trouble for yourself in the long run. Okay, so we've got t equals gamma, which is 1 over root 1 minus v squared, which was all of this guy, c divided by 2 squared over c squared multiplied by t0, which was 5. Now, usually a very good idea. This is getting very crowded. So instead, I highly recommend you just calculate gamma separately. So if we do that, we've got a half squared. So the c squared and the c squared are going to cancel. This is going to be a quarter. So 1 minus a quarter. So I've got 1 over 3 quarters. Yes, yes. Cool. Which will equal whatever it equals. Actually, no, we can do physics. We're in decimal approximation land. Cool. So we got 1 divided by the root of 3 divided by 4. Gives me 1.1547. Double check math. 1 divided by root 3/4. Yep. Cool. Okay, so what does that mean? Well, hopefully that means the time discrepancy would be about 15%, 15.5%. Cool. Okay. Well, did that. So we've got, keep dropping textile lids, 1.1547-ish multiplied by 5 equal, trying to hold too many things at once, multiplied by 5 gives me roughly 5.77 seconds. Super rough. Cool. Okay. Oh, okay. So what have we found? All right. Well, if we're on Earth, how long do we perceive the time on? Sorry, how long does it take for a clock on the rocket to tick to see 5 seconds on Earth tick by? So if you're on the rocket, it would take you 5.77 seconds to observe 5 seconds go past on an Earth clock. Okay, what if we do this the other way around? Okay. Oh, now we have to consider which one is the proper time. Alright, well now 5 seconds on the rocket. So now the event is moving with the rocket. So now this is t equals 0 on the rocket. And so this is time unknown. The velocity is all the same. You could say that it's negative if you wanted to say left and right actually matter. That's fine. Okay. Now, if we notice, all of these things are actually the same numbers. So we're going to end up with, the only thing you might not realize is if we have a negative velocity, we're going to square it. Square a negative becomes positive anyway. So we still get the exact same. Okay. So what does that mean? Well, t is going to equal roughly 5.77-ish seconds. So what's this saying? That's saying if you're on Earth, it will take 5.77 seconds for you to see the clock on the rocket tick over 5 seconds. Well, hang on. That seems contradictory. It took 5.77 seconds for the rocket to see 5 seconds tick on Earth, but when you're on Earth, it takes 5.77 seconds to see the rocket tick 5 seconds. How can those both be true? Well, this is the twin paradox in a nutshell. The basic gist of it is because you've lost track of simultaneity, because that doesn't exist. And the other part is we haven't done the full Lorenz equations. So you can have these things spit out and they are both true, which becomes problematic only if you decide that, oh, time goes past for everyone at the same rate, but it doesn't. So if you are observing an object move past you, right, or toward you or past you, it doesn't matter, move relative to you, you will see its clock ticking slower than your own. So if you observe something moving, it will appear to be moving slower through time than your own time. So that's the basic gist of that. Now, if that just sounds all weird and everything, that's perfectly fine, that's normal. It might take some of the other things that I've linked to really work through, but at the end of the day, the universe doesn't care if you like it or not. That just turns out to be the way things are. There's no such thing as a universal time, there's no such thing as simultaneity. Now, this leads on to the twin paradox, where, hang on, could we resolve this? Let's say we both have two people start with stopwatches and they both hit go, alright, and one travels off, accelerates to essentially the speed of light, travels off for a couple of years, spins around, comes back. Alright, brilliant. Now, if I'm the person on Earth, I've seen them speed off and come back, so I've seen them move, so I should think that their time is ticking slower. If I'm the person on the rocket though, from my perspective, the Earth moved away and then came back again. So they moved, so I'm going to see their clock ticking slower. But we both had clocks to begin with, so when the person out of the rocket comes out and they compare clocks, they both should be slower than each other. How does that make sense? That's a paradox, hence the name paradox. The trick to that, there's more subtle tricks to it, but the basic gist of it is we violated the inertial reference frame requirement. That rocket had to accelerate away and also accelerate back again. And so we've got accelerations in there. That breaks out as special relativity, and you need general relativity to do that, which is way outside of this course. So as a general rule, as soon as you have any sort of acceleration, you're done. You can't use special relativity anymore. There is a more in-depth explanation if you particularly care to go down the rabbit hole, which I'll link to. But I warn you that that's probably just going to scramble your brain more, but you're welcome to scramble your own brain. Cool. That's 6.2. This can take a fair bit of time just to work your way through, and usually it takes multiple visits before it'll actually begin to have some sense of normality about it. But that's that. Email me as you will inevitably get stuck, which is fine. Best of luck to you. See you next time.